What's up, algebros and broettes? We're doing math on the internet, so don't adjust your TV sets. Let's get linear. Okay, today we're going to take a look at Cramer's Rule, which is a very cool way to use determinants to solve a system if that system has a unique solution. So this won't work for infinitely many solutions, and won't work certainly if the system is inconsistent. So with Cramer's Rule, we have the following. Let A be an invertible n by n matrix, so a square matrix, for any vector B in vector space Rn, the unique solution x of Ax equals B has entries given by x sub I is equal to, it's the determinant of a sub I at B divided by determinant of A, and that's for I equals 1, 2, so on and so forth to n. And we'll talk about what that means, because we're going to actually be doing something a bit interesting with how we construct matrices and then how we build determinants from that. When using Cramer's rule, the matrix of cofactors is called the adjugate or classical adjoint of A, denoted by ADGA. And we have a formula that we're going to use at the end of today's lecture to talk about building an inverse matrix. So we have an inverse formula. Let A be an invertible n by n matrix. Then A's inverse, A inverse, is 1 over the determinant of A times the adjugate matrix of A. And we'll talk about how to build that adjugate matrix of A. There's a few steps to consider. We'll talk all about it, but that'll come after some Cramer's rule examples. Let's take a look at this example of Cramer's rule that we have here. Let me just sort of refresh what we're saying. So this system that we're going to start with, it's a 2 by 2 coefficient matrix. We have a vector in R2 that we're going to be working with. And when we build solutions, the solution should be for x1 and x2. So we're looking for two pieces to the solution. So if I actually want to write out how x1 and x2 are going to look, I can use this formula here. So x sub 1 is going to be the determinant of a sub 1 at B divided by the determinant of A. And x sub 2 is going to be given by the determinant of a sub 2 at B divided by the determinant of A. We'll have to talk about how we can find these pieces and build these pieces, but sort of keep that there handy. That's in particular how we're going to solve this system. Now the first thing that I want to do is I want to build the matrix A and the vector B, and it's not going to take too much work to do that. So matrix A is our coefficient matrix, and I can just look at the coefficients on x1 and x2 and place them in correct order. So the first row would be 5, 7 for the 5x sub 1 and 7x sub 2. And my second row is going to be 2, 4 for the 2x sub 1, 4x sub 2. So that's my matrix A. And then if I want to build the column vector B, well, that's the stuff that it's equal to, right? So B is 3, 1 as a vector in R2. Now that I have matrix A, one of the things I'm going to need is the determinant of A. So I can actually find the determinant of A right now. And here we know for the determinant of a 2 by 2 matrix, I multiply on the main diagonal. So that's 5 times 4. And then I subtract the product on the off diagonal. So minus 7 times 2. And what's that going to give me? Well, I'm going to get 20 minus 14. That's going to give me 6. So my determinant of A is 6. But there's some other pieces I'm going to need to build, and then some more determinants I have to find. Let's talk about what a sub 1 at B looks like. Now let me sort of explain this. This subscript, so it's a sub 1 at B, think of it like a functional notation as well. The subscript is telling me what column to replace, and I should be plugging into that column B as a column vector. So since this is a sub 1 at B, that means go to the first column of matrix A and replace that column with this vector B. So instead of 5, 2, this first column of A, I'm going to replace that first column 5, 2 with the column vector 3, 1. However, the rest of the matrix is going to stay the same. So I'm not replacing the second column, 7, 4. That stays as 7, 4. And similarly, I can do this to find a sub 2 at b. We sort of do it this way. A sub 2 at b. And this is saying, now go to the second column of matrix A, go to the second column of matrix A, and replace that with column vector B. So instead of the second column 7, 4, I'm going to replace that with the column vector 3, 1. But that my first column, which I'm kind of cutting it off here, but that's 5, 2, that first column, 5, 2, or any of the other columns for that matter, should stay the same as in matrix A. So that's the idea. I'm taking this matrix A, and I'm replacing one of the columns with column vector B. So A sub 1 at B, I replaced the first column with that vector B, but the rest stayed the same. For A sub 2 at B, I replaced the second column with that column vector B, but the rest stayed the same. That's the idea. That's how we want to treat this. Now that I found these two sort of special matrices, I want to find their determinants. So determinant of A sub 1 at B, multiply on the main diagonal, so that's 3 times 4 minus, and then multiply on the off diagonal, subtract that away, so minus 7 times 1. So that gives me 12 minus 7 gives me 5. If I want the determinant of A sub 2 at B, well, we can find that as well. We have the technology. So multiply on the main diagonal, that's 5 times 1 minus, multiply on the off diagonal, and we subtract that away, 3 times 2. Scooch down here, so that's going to give me 5 minus 6 is going to give me negative 1. Now I have all the pieces that I'm going to need to build my unique solution. So I'll say x sub 1, that's the determinant of A sub 1 at B divided by the determinant of A, which that's going to give me 5 on top, divided by determinant of the original matrix A was 6. Let's scroll up and show we did that work. And then x sub 2, the other piece of my solution, is the determinant of A sub 2 at B divided by the determinant of A. And A sub 2 at B's determinant was this negative 1, divided by determinant of A, I can look over there, it was 6. And now I have my pieces. So my solutions, x sub 1 is 5 over 6, x sub 2 is negative 1 over 6. And this is my unique solution. Or if I want to write this as a vector, I think it's fine just to write out the separate pieces to the answer, but if you want to see it as a vector, you could say vector x is this vector with entries x1 and x2 in order, 5/6, negative 1/6. And that's it. Hey, that's Cramer's rule. Very cool, very interesting. Let's see another example of a 2x2 system. So use Cramer's rule to find the solution to the following system. Remember, we start by building matrix A, and that's just our coefficient matrix. So the first row should be 3. So I have 3x1 minus 2x2 equals 7. So the first row should be 3, negative 2. Second equation is negative 5x1 plus 6x2 equals negative 5. So that second row of matrix A should be negative 5, 6. We remember building these coefficient matrices earlier in the course. And then vector B, that's the stuff we're equal to. So 7, negative 5. So not really new information, just the way that we arrange it, the way that we display it in this array, and this vector is different. So, okay, so we got that stuff out of the way. Now I can find the determinant of matrix A. Multiply on that main diagonal, 3 times 6, and then subtract the product on the off diagonal. That's negative 2 times negative 5. We can just go right through this. 3 times 6 is 18, minus negative 2 times negative 5 is 10. So that's going to give me 18 minus 10 is going to give me 8 for my determinant. And now I can start building these other two matrices that I need. I'm going to need A sub 1 at B. So it says go to matrix A, but go to the first column and substitute in that column B as a column vector. So this first column, 3, negative 5, I'm going to swap it out with B, which is this column vector 7, negative 5, and leave the rest of the matrix alone. So that means, well, my second column, namely, is going to stay the same, negative 2, 6. And we can do the same to build A sub 2 at B. So now this means go to the second column of A. Second column is this negative 2, 6. replace that with column vector b, which is 7, -5. But leave the rest of the matrix alone. So in particular, leave that first column alone, which was 3, -5. Just rewrite that. That one doesn't change. And now I can find the determinants for these. Okay, so we'll find the determinant of a sub 1 at b. So we'll multiply on the main diagonal, so 7 times 6 minus the product on the off diagonal, -2 times -5. So 7 times 6 is going to give me 42, minus, and then -2 times -5 is 10, so that's going to give me 32. And the determinant for a sub 2 at b, multiply on the main diagonal, so that's 3 times -5, and then subtract the product on the off diagonal, which is 7 times -5. And we can compute this. So this is going to give us -15, and then minus a negative is plus 35, and that's going to give us 20, positive 20. And now I can build my two parts to my solution, where x sub 1 is the determinant of a sub 1 at b divided by the determinant of a. And that's going to give me 32 divided by 8, right? Determinant of a, we found that at the very start, that was 8. And this reduces, right? Gives me 4. And x sub 2 is the determinant of a sub 2 at b divided by the determinant of a, which is going to give me 20 divided by 8. And I can reduce this by 4 on top and bottom. 4 goes into 20 5 times. 4 goes into 8 twice. So 5 halves. And this is the solution to our system. So we should write x sub 1 equals 4. X sub 2 equals 5 halves. There's our unique solution to the system. We have our unique solution. Not bad. Let's take a look at another example. Let's take a look at a larger system. Let's take a look at 3 equations, 3 unknowns. So I have 2x1 plus x2 equals 7, -3x1 plus x3 equals -8, and x2 plus 2x3 equals -3. Now when building matrix A, be on the lookout for any missing term. Because when I go to build my coefficient matrix, here this first row, I'm missing x3. So it's 2x1, 1x2, and then it would be a 0x3. Since it's missing, its coefficient must be 0. For the second row, I have a -3 times x1, so -3x1, and I'm missing x2. I don't see any x2, so that would have to be a 0x2, and then 1x3. And then for this last equation, well, I'm missing x sub 1. So starting off, that would have to be a 0x sub 1. But then I have 1x sub 2 and 2x sub 3. So there's my coefficient matrix A. And my column vector B is the stuff that we're equal to. So that's 7, -8, -3. Okay. Now I want to find the determinant of A. In this case, I'm just going to go through a cofactor expansion. I'm going to do a cofactor expansion across the top row, just a classic cofactor expansion. Remember that checkerboard pattern, though. Don't forget the sign, plus, minus, plus, and then it would be next row minus, plus, minus, and then plus, minus, plus. I have to be responsible for that. And that's going to come up later when we talk about inverses as well. But here, when I bring out this 2, moving along the top row, 2, 1, 0, when I bring out the 2, I don't want to flip its sign. So we'll say determinant of A. Bring out the 2. And then I want to multiply by the determinant of the 2 by 2 matrix that I get when I remove that entries row and column. So that's 0, 1, 1, 2, red row-wise. Then next, when I bring out this 1, since the sign associated with it is this minus sign, that doesn't mean necessarily it should be negative or anything like that. Remember, that means I just want to flip the sign. So if it were negative, make it positive. Since it's positive, I'm going to make it negative. We flip the sign. So that's going to be, bring it out as a -1. And then times the determinant of the 2 by 2 matrix that I get when I remove that entries row and column. I think it's nice to sort of line up a couple pens or pencils to crosshair that entry so that we can see what's left, but that would be the -3, 1, and the 0, and the 2. And the rest of the cofactor expansion, I'm bringing out a 0, and that's just going to kill off whatever the determinant is. So I don't even care about that. So we would just sort of skip over that. We like to pick a row or a column that has a lot of zeros in it. In this case, there's a lot of options. This is one of them. And let's go through the 2 by 2 determinants now, because we can compute this. So we have 2 times, here the 2 by 2 determinant, 0 times 2 is 0, minus 1 times 1 is 1, and then minus 1 times, we have negative 3 times 2 is negative 6, minus 1 times 0 is 0, and I can go ahead and compute this determinant through. So 2 times negative 1 is negative 2, and then I get minus negative 6 is plus 6, so this is going to give me 4 for the determinant of A. From here, I'm ready to talk about the other pieces that I need, and I have to build those. So first I want A sub 1 at B. And remember what this means. This means go to the first column and replace the first column with column vector B. Now what was the first, what is vector B, I should say? That's 7, negative 8, negative 3. It goes into my first column. But the rest of the columns stay the same. So columns 2 and 3, namely, are going to stay the same as they were in matrix A. So that's second column, 1, 0, 1. LOL. And then a third column, 0, 1, 2. And then I want to go ahead and find the determinant of this. So let's go ahead, let's find the determinant of it, and then we'll go back, we'll find the next one. We'll sort of keep the work set up that way. So now what I want is I want to do a cofactor expansion. I'm just going to go along the top row again, since it still has a 0 I can utilize. So I'll say, okay, determinant of A sub 1 at B. Remember the checkerboard pattern. I'm going to bring out the 7. I'm not going to flip its sign. Times the determinant of the 2 by 2 matrix that I get when I remove that entries row and column. That's 0, 1, 1, 2. Then I'm going to bring out the 1, but I have to flip its sign, so it's negative 1, times the determinant of the 2 by 2 matrix that I get when I remove that entries row and column. So that's going to be negative 8, 1, negative 3, 2. And then the rest of it, I'm bringing out a 0 so I can sort of skip over that. That's the luxury that I get to take. And so let's compute this. So I have 7 times 0 times 2 is 0, and then minus 1 times 1 is 1, and then negative 1 times negative 8 times 2 gives me negative 16, and then minus a negative 3, so that's plus 3. And then we can go ahead and compute this through. So let me go ahead and expand this out a bit. 7 times negative 1 is negative 7. If I bring this minus 1 in, I'm going to have minus negative, so that's plus 16, and then minus 3. And I'll say, okay, negative 7 and negative 3 give me negative 10, plus 16 gives me 6. And I'll have to go and find the other pieces that I need, so I'm just boxing these, circling them for now, but I'll go ahead and find these pieces and assemble my final answer when I'm ready for it. Let's go ahead and now take a look at A sub 2 at B. So I have to build this matrix, but this is telling me to go to the second column of matrix A, right in the middle, since it's a 3 by 3 matrix, and replace that with the column vector B. What was that column vector B again? That was 7, negative 8, negative 3. But that the rest of the matrix should stay the same. So column 1 and column 3 should be the same as it was in A. I'm only replacing column 2. So what was column 1? Column 1 was 2, negative 3, 0. Column 3, what was that? 0, 1, 2? Just the numbers in order like that. Yeah, 0, 1, 2. Now I want to find the determinant of this matrix. All right. Not a big deal. We can do that. And here I can still take advantage of, a cofactor expansion along the top row. There are other ways that I could do cofactor expansions that utilize a 0. But I'm a fan of that classic cofactor expansion if it looks good. So I bring out the 2. I don't change its sign. Times the determinant of the 2 by 2 matrix that I get when I remove that entries row and column. That's negative 8, 1. Negative 3, 2. I bring out the 7. I have to flip its sign because of where it is in the matrix. And then I want to multiply that by the determinant of the 2 by 2 matrix that I get when I remove that entries row and column. So that's negative 3, 1, 0, 2. And now I can compute this. So what is this? I get 2 times negative 8 times 2 is negative 16. And then minus negative 3 is plus 3. And I have minus 7 times negative 3 times 2 gives me negative 6. And then minus 1 times 0 is 0. So what do I have here? This is 2 times, and then negative 16 plus 3 is negative 13. And then I have minus 7 times negative 6. I'm just working through the arithmetic. So here this is going to give me 2 times negative 13 is negative 26, and then plus 42. And then that is going to give me 16, it looks like. And there's one more of these I have to go through, and then I can start assembling my solution. So we have to build A sub 3 at B. One more 3 by 3 matrix and one more determinant. We'll have all the pieces. And this is telling me, okay, go to the third column and replace the third column with that vector B. So I'll say, okay, I think I remember it was 7, negative 8, negative 3. Is that what it is? 7, negative 8, negative 3 is what it is in that third column. But the rest of the matrix, columns 1 and 2, should stay the same. What was column 1? Column 1 was 2, negative 3, 0. And column 2 was LOL. So 2, negative 3, 0. Where the first column is stays the same. 101 for that second column. And this is how A sub 3 at B should look. And I want the determinant of this. Cat is here to help. Cramer's Rule. Now for this, you can do a cofactor expansion across the top row. That's fine. But if you're looking to maybe take a bit of an easier way about this, let me do down column 2. So I got a nice cofactor expansion. I think I appreciate that. Determinant of A sub 3 at B. Remember the checkerboard pattern. Never hurts to rewrite it if you don't remember it. When I bring out this, so I'm down this second column, 1, 0, 1. I'm going to skip over the 0 though, because it's not going to stick around for very long. When I bring out this 1, I have to flip its sign. So that's negative 1 times the determinant of the 2 by 2 matrix that I get when I remove that entries row and column. So that's negative 3, negative 8, 0, negative 3. Skipping over the 0, though I wouldn't flip its sign, but it's signless. And I'm going to go to this last entry, which is this 1. I have to flip its sign because of that checkerboard pattern. So minus 1 times the determinant of the 2 by 2 matrix that I get when I remove that entries row and column. So that's 2, 7, negative 3, negative 8. Let's see what we get. So negative 1 times negative 3 times negative 3 gives me 9, and then minus 0. And then here I have negative 1 times 2 times negative 8 is negative 16. And then here I'm going to have minus a negative 21, so that's plus 21. And we can compute this. So here I have negative 9, and then minus 1 times here. 21 minus 16 is going to give me 5. So negative 9 and then minus 5 is really what this is, gives me negative 14. Just go ahead and circle it. So I should have all my pieces. I found them, I circled them all. We're ready to build the parts to our solution. X sub 1 is the determinant of A sub 1 at B divided by determinant of A. X sub 2 is the determinant of A sub 2 at B divided by the determinant of A. And X sub 3 is the determinant of A sub 3 at B divided by determinant of A. I'm just getting ready to drop in all of the parts that I have for my work. So what was the determinant of A, the original matrix? We found that to be 4, and the determinant of A sub 1 at B was 6. So determinant of A was 4, determinant of A sub 1 at B was 6, and in fact determinant of A is in the bottom of all of these fractions. So 4 is in all the denominators. What about the determinant of a sub 2 at b? We found that to be 16. That should be my second piece's numerator. And determinant of a sub 3 at b, we found that last was negative 14. And now I can reduce these. So here, 6 divided by 4, I can reduce the top and the bottom by 2, so that's 3 halves. 16 divided by 4 divides cleanly, gives me 4. And negative 14 over 4, I can divide the top and the bottom by 2, gives me negative 7 over 2. So we have x sub 1 is 3 halves, x sub 2 is 4, and x sub 3 is negative 7 halves. This is my unique solution to the system. I can compute this using determinants. Let's take a look at another example of Cramer's rule before we talk about building inverses with the adjugate or the classical adjoint matrix. Let's take a look at something that's similar computationally, but with a little bit of an idea behind it. For the following system, I'd like to determine the value for the parameter alpha for which the solution has a unique solution and describe the solution. And here I'm given the system alpha times x sub 1 minus 2 alpha x sub 2 equals negative 1. And then another equation, 3x sub 1 plus 6 alpha x sub 2 equals 4. Now I'm going to start off just doing what I've been doing with Cramer's rule. I can describe the solution that way. So matrix A, I'm going to build this as my coefficient matrix, and it's in terms of this unknown alpha. So here the first coefficient would be alpha, and then the next entry in that row would be the minus 2 alpha. And for my second row, well, it's going to be 3, and then 6 alpha. And I can build that column vector B, the stuff that we're equal to, right, is negative 1, 4. Now when I go to find the determinant of this matrix A is where we can start part of that conversation. Determinant of A, I'm going to have alpha times 6 alpha, and then minus negative 2 alpha times 3. And you can say, well, what is this going to give me? Alpha times alpha is alpha squared, so I have 6 alpha squared. Minus a negative is plus 6 alpha. And I would say, well, factor this. So I can factor out a 6, and I can factor out an alpha, and that leaves me with, in parentheses, alpha plus 1. So this is my determinant of A, is 6 alpha times alpha plus 1. And there's some comments that I can make here. In order for this to have a unique solution, I would need to make sure that my coefficient matrix is invertible. And we can think about then solving the system, right? Ax equals b. Jot some ideas up here. I think about solving Ax equals b with unique solution by multiplying both sides by A inverse. And saying, well, A inverse times A gives me the identity times x equals A inverse b, so that my unique solution x is A inverse times b. So in order to find this unique solution, I would need A to be invertible. For A to be invertible, I need to make sure that its determinant is non-zero. We just talked about this. This is sort of a continuation on our invertible matrix theorem. So really, the only issue that I'm concerned about is if my matrix is non-invertible, which means I'm concerned that my determinant might be 0. And that could happen here. So let's switch over to the red. Red means no. I want to make sure that alpha isn't 0, or that alpha plus 1 does not equal 0, which means alpha should not be negative 1. And that's because I want to make sure that my determinant does not equal 0. I want to make sure that this 6 alpha times alpha plus 1 is non-zero, which really falls into these two possibilities. So no matter what I have for alpha, shouldn't be 0. That gives me a determinant of 0, which is bad news. Or it should not be a negative 1. If alpha is negative 1, that's also bad. It gives me a determinant of 0. I don't want that. I need to make sure I stay away from that. But provided alpha is anything else, if alpha is not 0, if alpha is not negative 1, anything else for alpha is fine, perfectly fine. So that's the consideration that we have here. There's another reason that we'll show as we're building our solution why that's important. It's something a bit more computational, We'll be able to show this in a couple ways why I want to make sure that determinant of A is non-zero. You're probably already guessing why that is. If you already know what we're going to talk about, let me know in the comment section below. Let's go ahead and build A sub 1 at B. So this means go to the first column, replace it with column vector B. Column vector B is negative 1, 4. The rest of the matrix stays the same, so the second column stays the same. Negative 2 alpha and 6 alpha. And then we can also build A sub 2 at B. Do this kind of alongside here, which means we'll go to the second column and replace the second column with column vector B. So negative 1, 4 in the second column. And then the first column of A should stay the same, which was alpha 3. And find the determinants. Yes, of course. Determinant A sub 1 at B is going to be negative 1 times 6 alpha is negative 6 alpha. And then minus, this is going to be a negative 8 alpha. So minus a negative is going to be plus 8 alpha. That's going to give me 2 alpha. Combining like terms. And for the determinant of A sub 2 at B, we have alpha times 4 gives me 4 alpha, and then minus negative 3 gives me plus 3. And so this depends on what that parameter alpha is. But from here, I can build my solution. I can find a closed form for it. So we'll say, well, x sub 1 should be the determinant of A sub 1 at B divided by the determinant of A. Determinant of A sub 1 at B is 2 alpha. Divided by determinant of A, what was that? 6 alpha times parentheses alpha plus 1. I don't have a great memory, but I think that's what it was. 6 alpha times alpha plus 1. And I can reduce this. Right, so we're saying, provided that alpha is non-zero and not negative 1, so I'm not getting any division by 0, alpha some other value, I should be able to cancel alpha divided by alpha here on top where it's factored in the bottom and then present on top. And then the 2 over 6 is going to reduce as well. So I'm left with a 1 on top, and then 2 over 6 gives me that 3 on bottom. The alphas here cancel, and then I still have this alpha plus 1 in parentheses on bottom for x sub 1. And for x sub 2, well, similar idea. This is determinant of A sub 2 at B divided by determinant of A. The determinant of A sub 2 at B, we saw that was 4 alpha plus 3. Divided by determinant of A was 6 alpha times parentheses alpha plus 1. And this isn't going to reduce, unfortunately, right? Not unless I know some more information about what we have for alpha. But there is a consideration I want to make sure that I'm clear about. We said we'd talk about it. Notice we're dividing by the determinant of A. I'm dividing by 6 alpha times alpha plus 1. If this determinant is 0, and I'm dividing by it, that's a big issue. I can't divide by 0. We're not allowed to divide by 0. Don't you ever divide by 0. If I find that you're dividing by 0, I'm going to find out, and I'm going to be very upset with you, so don't divide by 0. So there's a second consideration here. Even if we forget perhaps the information about the invertible matrix theorem, that I need A to be invertible to find this unique solution, we can see the faux pas in a computational sense, that I'm not supposed to be dividing by 0, and that this would create a big issue. So we can then go ahead and make some comments. We'll say, well, here's our solution. We get a different color here. You like the baby blue? X sub 1 is going to be 1 over 3 times quantity alpha plus 1. And x sub 2 is going to be 4 alpha plus 3 divided by 6 alpha times quantity alpha plus 1. But this is, along with the following, alpha cannot be 0 or negative 1. As long as that's the case, this is good, and this is how my solution looks. And this is kind of an interesting approach to a system, to solving it, because if I had a system that was always going to stay in this generic form, but the parameter alpha would change, we'd say, well, as soon as I set that parameter and I know what alpha is, I can go ahead and plug in provided it's not 0 or -1, and plug in to find the two parts to my solution. But then if I want to go back and still have a system of this form, but I want alpha to now be something different, then I can do the same. I'll say, okay, well, what if alpha is, we said it can't be 0 or -1. What if alpha is 7? Well, now I've already done the work. I can plug 7 in for alpha. Well, what if alpha happens to be -5? Well, my system changes, but I can still find the solution by substituting in. So perhaps useful. Okay, let's take a look at just a bit more. Let's take a look at finding inverses using the adjugate. So here we're going to find the adjugate of the given matrix. We're going to use our theorem to find the inverse of the matrix. And here we have an inverse formula. Let A be an invertible n by n matrix. Then the inverse, A inverse, is 1 over the determinant of A times the adjugate of A, or sometimes referred to as the classical adjoint of A, though that just might be older texts. Let's talk about what this adjugate matrix is. Let's talk about what this adjugate matrix is. The adjugate matrix of A is the transpose of the cofactor matrix of A. Okay, so there's some things that we have to consider. So what do we want to do? First, find the cofactor matrix, which we denote capital C, and that would be of A. And the cofactor matrix of A, call it capital C. Second, I want to transpose the cofactor matrix capital C. And here C transpose is the so-called adjugate matrix of A. And then for the third step, finding A inverse, where A inverse is 1 over the determinant of A scaled into the adjugate matrix of A. So there is a step somewhere in here where I have to be finding the determinant of matrix A. We'll do that at the beginning. But this is the basic idea. I need to find my cofactor matrix C, find the determinant first of A, but then I want to find the cofactor matrix of A. I want to transpose that, and then I want to scale that transposed cofactor matrix by 1 over the determinant of A. Okay, so we've got a lot to talk about. Let's talk about the cofactor matrix. To build a cofactor matrix, it is going to be a matrix that is of the same size as the square matrix that we're starting with. So here I have this matrix A. It is a 3 by 3 matrix. My cofactor matrix C is also going to be a 3 by 3 matrix. Something that's very important for the cofactor matrix, though, is the sign from the checkerboard pattern. So I am going to write that again. So top row is plus, minus, plus. Second row is minus, plus, minus. Third row is plus, minus, plus. Don't forget that checkerboard pattern. Now the cofactor matrix, once you get comfortable building it, it will go a bit faster. But just to sort of illustrate how we find it, I am going to belabor the process to start. This first entry in the first row, I go to this 3, and I'm not going to pick it out. So this is different than a cofactor expansion to find a determinant, but there's some parts of it that are still left behind. I'm not going to pick out the 3. That builds a linear combination of cofactors. I don't want a linear combination of cofactors. I just want the cofactors. So instead of picking out that 3, what I'm going to do is I'm going to go to this first entry, upper left corner, and sort of crosshair it, get rid of that entry's row and column, and then I want the cofactor that would be left, and that's the determinant of the smaller matrix. So that smaller 2 by 2 matrix would be this 0, 1, 1, 1. And I want to find the determinant of this. I'll do D for determinant. I'll do that in the next step. I don't flip its sign because associated with a plus sign. Now I'm going to move on to the next entry in the row. This has a minus sign associated with it, so I'm going to have to flip some sign somewhere. Don't let me forget. But I want to do the same thing. So the 5 is there. I don't care about the 5 though. I'm not going to write it. but I am going to remove that entry's row and column and find the determinant of that smaller 2 by 2 matrix. And that's going to be 1, 1, 2, 1. And I have to flip the sign because of my checkerboard pattern. I want D for determinant, sure. And then now for the third entry, I don't have to flip any sign, so that's good. I'm going to go to the 4. I'm not going to write the 4. That's a bit different than finding a determinant. We're just worrying about the cofactor. Remove that entry's row and column, and then I want the determinant of the 2 by 2 matrix that is left when I remove that entry's row and column, so that's 1, 0, 2, 1. I want the determinant of this, so D for determinant, or DET. If I had confidence that I had more space, I would write DET. Now we continue this. So now I'm going to go to this 1 here, right? First entry of the second row. I have to flip some sign, but if I remove that entry's row and column, I have the 2 by 2 matrix 5, 4, 1, 1. I want the determinant of it, but I have to flip the sign. Go to the middle, smack dab in the middle. That's the 0. I'm not going to pick out the 0. But I'm going to remove that entry's row and column, and that's going to give me 3, 4, 2, 1. I want the determinant of that. I don't have to flip the sign. And then now, last entry of the second row, I'm not going to pick out the value. I'm going to remove its row and column though, and that leaves me with 3, 5, 2, 1. I want the determinant of that. But I am going to have to flip the sign because of where it lays in the 3 by 3 matrix, my sign pattern, that checkerboard pattern. We have one more row to go. And then we have to compute these determinants too. So here, first entry of the third row, I got the 2 there. Don't pick out the 2, but remove its row and column. That leaves me with the matrix 5, 4, 0, 1. Find its determinant. And because there's a plus sign associated with it, I don't flip the sign. Now move along. There's this 1. Don't bring out the 1. You don't have to worry about that stuff. That's only for finding a determinant, which is a linear combination of cofactors. Here we're just doing the cofactors. Remove that entry's row and column. It leaves me with 3, 4, 1, 1. Find the determinant of that matrix. But I am going to have to flip the sign because of where it is in my checkerboard pattern. And then one more to go. Don't bring out the entry, bottom right corner, but do remove that entry's row and column. It leaves me with the matrix 3, 5, 1, 0. I want the determinant of that, and I don't have to flip the sign because of where it is. This is how we build that cofactor matrix. Now I have to start finding determinants. Determinants of 2 by 2s aren't so bad, so we can do that. So here I'm going to get 0 minus 1 gives me negative 1. Here I'm going to get 1 minus 2 gives me negative 1, but I have to flip the sign, so that's going to become positive 1. So determinant is a negative 1. But don't forget to flip the sign there. And for this last one, I get 1 minus 0 gives me 1, and I keep it. Don't flip the sign. So on and so forth. So now here, I'm going to have determinant 5 minus 4 is 1. I have to flip the sign, so that's now negative 1. Next, I'm going to have 3 minus 8 gives me negative 5, and I keep it the way it is. Then next, I'm going to have 3 minus 10. 3 minus 10 gives me negative 7, but I have to flip the sign to a positive 7. Then last row, 5 minus 0 gives me 5. Keep it the way it is. Next, I have 3 minus 4 gives me negative 1, but I got to flip the sign, so it's positive 1. And then here I have 0 minus 5 is negative 5, and I keep it the way that it is. So there's my cofactor matrix. What did I have to do? I had to find the smaller determinant, and I had to either keep or flip the sign based on my checkerboard pattern. And this is all of my work sort of supplied there. Now that I have the cofactor matrix, I want to find the transpose of this. Now for the transpose of the cofactor matrix, what I'm going to want to do is just rewrite the columns as rows and vice versa. So this first row, negative 1, 1, 1, becomes my first column, negative 1, 1, 1. Second row, negative 1, negative 5, 7, becomes my second column, negative 1, negative 5, 7. And my third row becomes my third column. So 5, 1, negative 5 was my third row. 5, 1, negative 5 becomes my third column in the transpose. So now I have the transpose of my cofactor matrix, which is the so-called adjugate matrix of A. Now, one thing that I said I was going to do that I didn't do yet is actually find the determinant of this matrix. Let me rewrite the matrix and find its determinant. Since that is my fault, I should have done that, but I did not do that. Let me rewrite matrix A. 3, 5, 4, 101. And then that third row, 2, 1, 1. And you know, and just any cofactor expansion is fine. I have to find the determinant. So for the determinant of A, I'm going to go across the second row. That looks really nice. 1, 0, 1 doesn't look so bad. Don't forget the checkerboard pattern. When I bring out this 1, I'm going to need minus 1 times the determinant of the 2 by 2 matrix. So lots of cofactors, right? That's going to be the matrix 5, 4, 1, 1. Could even use some of my previous work above to help out. And then next would be a 0 that I bring out. And then next I'm going to bring out that 1. I got to flip its sign times the determinant of the 2 by 2 matrix when I remove that entry's row and column. So that's going to give me 3, 5, 2, 1. You could do any cofactor expansion how you would like, any row, down any column, sure. So I'm going to get negative 1 times, here I have 5 minus 4. Ditch the 0, and then minus, here I'm going to have 3 minus 10. So this is going to give me negative 1 times 1 is negative 1, and then minus 3 minus 10 is negative 7. Negative 1 plus 7 gives me 6. So I have 6 is the determinant of the matrix A. I should have found that at the beginning, but doesn't matter. No, I got it now. So then A inverse, I have all the pieces. That's 1 over the determinant of A multiplied into the adjugate matrix of A. So here I can sort of set up to find this. That's 1 over 6 times my adjugate matrix, which I just found above here. So that had rows negative 1, negative 1, 5. And then 1, negative 5, 1. And then 1, 7, negative 5. Don't leave it like this. Don't be lazy. You're not. I don't consider you to be a lazy person at all. This is just communication expectations, right? Bring in that determinant. Don't leave this as a scalar times a matrix. Just write your answer as a matrix. A inverse. None of these things will reduce cleanly. So in fact, the work is actually not so bad. It's going to be negative 1 over 6, negative 1 over 6, 5 over 6 for the first row, 1 over 6, negative 5 over 6, 1 over 6 for the second row, 1 over 6, 7 over 6, negative 5 over 6 for the third row. And that is my inverse. That is A's inverse. Hey, pretty cool. We'll take a look at one more example of this. I think it's not a bad idea if you want to pause the video and try to find the inverse using the adjugate by building the cofactor matrix, finding the transpose of it, all of that stuff. And then resume the video. We'll take a look at it together and let me know in the comment section below if you got it right or if you had a small arithmetic mistake. Let me know that too. And welcome back. Let's find the determinant of this matrix first. This is a lower triangular matrix because I have this slice of zeros here above the main diagonal and my non-zero, well, my primarily non-zero entries beneath the main diagonal. We talked about these triangular matrices before. So this is a lower triangular matrix. So it's the product of the entries on the main diagonal that's going to give me my determinant. Or you could do a cofactor expansion, right? So 3 times 1 times 2 is my determinant, which is 6. Same as the last one, I think, right? Determinant of this matrix is also 6. Don't forget that checkerboard pattern. Do a little reminder. Every little bit helps. Let's build the cofactor matrix. I'm going to go a little bit faster with this. Here where that 3 is, remove that entries row and column. For the determinant, I get 2 minus 0 is 2. Keep it, don't flip the sign. Next, go to that 0, remove the entries row and column. So here, from sort of visualizing it, we get determinant negative 2 minus 0, which is negative 2, but I have to flip the sign, so it's now negative 2 is positive 2. Go to that last 0 in the top row, remove that entries row and column. The determinant is going to be negative 3 minus negative 2, which is negative 3 plus 2, which is negative 1. And then I don't flip it, so that's going to be negative 1. Now, I can go to the second row, remove that negative 1's row and column, don't pull anything out. And then here I'm going to have determinant 0 minus 0 is 0, and I flip its sign, but it's still 0. Go to this 1 right smack dab in the middle, remove that entries row and column. Determinant is going to give me 3 times 2 minus 0 times negative 2, so 6 minus 0 is 6. And I keep it, I don't flip it, so 6. Then go to this 0, I'm not bringing anything out, this isn't a cofactor expansion, it's just cofactors. But remove that entries row and column, and then determinant is 3 times 3 minus 0 times negative 2, so that's 9 minus 0 is 9. I'm going to have to flip the sign on it, so that's negative 9. Now, last row, so go to that negative 2, don't bring it out, but remove its row and column. Determinant is 0 minus 0, which is 0. Go to the 3, don't bring it out, but remove its row and column. Determinant is 0 minus 0, which is 0. And I have to flip the sign, but it's 0 anyways. Last cofactor, go to the 2, don't bring it out, but remove its row and column. The determinant of that 2 by 2 matrix that I'm left with is 3 minus 0, which is 3, and keep it. Don't flip it. We notice that building this cofactor matrix did something interesting with our triangular matrix, worth pointing out. But now we transpose. So the adjugate matrix, which is the transpose of the cofactor matrix, means we're going to exchange rows for columns and vice versa. So the first row, 2, 2, negative 1, becomes my first column, 2, 2, negative 1. Second row, 0, 6, negative 9, becomes my second column. And the last row becomes my last column, 0, 0, 3, in that order. And this transpose of the cofactor matrix is the adjugate matrix. But now to find the inverse, A inverse, I want to scale this by the determinant of A. Determinant of A we'll scale it by 1 over that, right? Determinant of A is 6. So I should divide each of these entries by 6. I'll do it first literally, so 2 over 6, 0 over 6, 0 over 6, 2 over 6, 6 over 6, 0 over 6, negative 1 over 6, negative 9 over 6, 3 over 6. But if we can, we should reduce, and we will. So A inverse, let me know if this is what you got in the comment section below. 2 over 6 gives me 1/3 if I reduce. 0 divided by 6 is 0, and then again. 2 over 6 is 1/3. 6 over 6 is 1. 0 over 6 is 0. Negative 1 over 6 does not reduce. Negative 9 over 6 I can reduce by 3 on top and bottom, so that's going to give me negative 3 over 2. And 3 over 6 reduces to 1/2. So this is my inverse matrix of A. I get rows 1/3, 0, 0, 1/3, 1, 0, negative 1/6, negative 3/2, 1/2. Now something that I want to just mention before finishing this lecture, because we're just about done, just about out of time, is that this isn't a new process for us necessarily. You might think, well, this is a crazy way to find an inverse. We talked about building inverses of 2 by 2s. We talked about sort of this augmentation with an identity matrix and then row reduction to push the identity to the other side. But this classical adjoint or adjugate construct is exactly what we do when we build our 2 by 2 inverse, that closed form that we have. And let me sort of show. So if I have a matrix A, and just a generic one with rows AB, CD, we say, well, the determinant of this matrix A is defined as A times D minus B times C. I can start this process. Now, don't forget the checkerboard pattern, though it's very small in this one. It's just plus, minus, and then minus, plus. But if I build my cofactor matrix, Say, we'll go to the first entry, remove its row and column. That just leaves me with D. So I just write D. Go to the second entry in the second row, in the first row, second entry, first row. Remove that entry's row and column, leaves me just with C, but I have to flip the sign on it, so minus C. And go here to the second row, first entry, remove that entry's row and column, leaves me with B, but I have to flip the sign on it. And then here, last entry, remove its row and column, leaves me with A, don't flip the sign. So there's my cofactor matrix. But then we transpose this. Say, well, what happens if I transpose it? Well, now my first row becomes my first column, so first column is D negative C. Second row becomes my second column, negative BA. And now what I want to do is I want to scale this by the determinant. So we'll say, okay, so then 1 over the determinant of A times the adjugate of A is equal to A inverse, and that's 1 over, remember the determinant was AD minus BC, times this adjugate matrix, which is the transpose of the cofactor matrix with rows D minus B minus CA. So it's the same process, right? We said matrix A had rows A, B, C, D. It's that same colloquial process. We say, okay, on the main diagonal, swap those entries. Put D where A was and A where D was. On the off diagonal, keep those entries where they are, but change their sign, and then divide by the determinant. So this isn't a brand new process. We just haven't seen it for larger matrices. This is what we do when we find the determinant of a 2 by 2 matrix. We treat it as a formula, right? Much easier to do that for sure, but it actually comes from this adjugate matrix. Hey, thank you so much for hanging out with me. No matter where you are and what you're doing, remember to always keep learning, keep dreaming, to always follow your heart. And I will see you next time. We're going to do some more math. But until then, take care of yourself. And I will see you next time.